At 30,000 feet, the atmosphere is simply too thin to sustain efficient internal combustion. Whilst conventional designers struggled with mechanical supercharger limitations, Alexander Kartveli committed to the exhaust-driven turbine. This is the technical reality of how he integrated the massive Pratt & Whitney R2800 radial engine with a complex turbosupercharger system, engineering a heavy fighter capable of dominating extreme altitudes. The fundamental limitation of any naturally aspirated aviation engine is altitude. At 30,000 feet, atmospheric pressure is roughly 1/3 of that at sea level. Without forced induction, the mass of oxygen entering the cylinder is insufficient to maintain the stoichiometric ratio required for high power output. European designers primarily countered this with gear-driven centrifugal superchargers. However, operating at extreme altitudes necessitates extremely high supercharger impeller speeds to achieve the required manifold pressure. This mechanical connection exacts a severe parasitic toll. Driving a supercharger at 30,000 feet can drain hundreds of horsepower directly from the engine's crankshaft. Alexander Kartveli, evaluating the requirements for the Republic P-47 Thunderbolt, recognized that this parasitic loss was aerodynamically and thermodynamically inefficient for a heavy, high-altitude interceptor. His solution lay in recovering waste energy. An internal combustion engine expels approximately 1/3 of its fuel energy as heat and kinetic energy through the exhaust. A turbosupercharger captures this expelled energy. By routing the high-velocity, high-temperature exhaust gases through a turbine wheel, the system drives a connected centrifugal compressor. This compressor forcefully inducts thin, high-altitude air, densifying it before feeding it to the carburetor. Because the compressor is entirely decoupled from the engine's mechanical gear train, the parasitic horsepower loss is virtually eliminated. The engine maintains its sea-level rated power output at altitudes where conventionally supercharged engines rapidly degrade. Kartveli selected the Pratt & Whitney R2800 double Wasp as the primary power plant. This was an 18-cylinder, twin-row radial engine displacing 46 litres and producing 2,000 horsepower. Integrating a turbo-supercharger with an engine of this displacement presented an unprecedented spatial and thermodynamic challenge. The turbo-supercharger unit itself was massive. The turbine wheel had to operate reliably whilst spinning at upwards of 20,000 revolutions per minute, continuously subjected to exhaust gas temperatures exceeding 800 degrees Celsius. Furthermore, the act of compressing the intake air generated intense friction and heat. To prevent catastrophic pre-ignition within the engine's cylinders, this highly compressed charge required a massive intercooler to drop its temperature before it reached the carburetor. Conventional design philosophy involved attempting to package these components within or immediately behind the engine cowling. Kartveli deduced this was physically impossible without creating insurmountable aerodynamic drag and fatal thermal management failures. His radical decision was to abandon conventional fighter architecture entirely. He designed the P-47 Thunderbolt not as a traditional aerodynamic fuselage, but as a rigid structural envelope surrounding a massive, complex network of thermodynamic plumbing. He placed the heavy turbo-supercharger assembly far aft in the fuselage, well behind the cockpit. This decision resolved the center of gravity issues created by the heavy R2800 engine up front, but it dictated the Thunderbolt's characteristically deep, elliptical cross-section, setting the stage for the most extensive ducting network ever placed in a single-engine fighter. Having positioned the massive General Electric turbo-supercharger in the rear fuselage, Alexander Kartveli faced the primary thermodynamic challenge, transporting the volatile exhaust gases from the engine to the turbine without destroying the airframe. The Pratt & Whitney R2800 expelled exhaust gas at immense volumes and temperatures exceeding 800 degrees Celsius. Kartveli designed a dual exhaust collection system. The gases were gathered at the engine block and channeled into two large-diameter, heavily insulated pipes. These pipes ran the entire length of the lower fuselage, passing directly beneath the pilot's cockpit floor to reach the aft-mounted turbine. This routing created a severe mechanical hurdle: thermal expansion. Steel ducting, subjected to such extreme temperature variations, will expand and contract significantly along its length. If these pipes were rigidly fixed to the airframe, the expansion would buckle the internal structure of the fuselage. Kartveli resolved this by engineering articulated expansion joints within the exhaust piping. These slip joints allowed the ducting to lengthen and shorten dynamically without transmitting stress to the surrounding aluminium bulkheads. Furthermore, extensive thermal shielding and strategic ventilation were required to ensure the radiant heat from these pipes did not roast the pilot or compromise the adjacent hydraulic and electrical systems. Before reaching the turbine, the exhaust system incorporated a critical control mechanism: the wastegate. To regulate the engine's manifold pressure, this butterfly valve allowed a precise volume of exhaust gas to bypass the turbine entirely and exit directly into the atmosphere. By articulating the wastegate, the pilot, and later automated boost regulators, could dictate the rotational speed of the turbine, preventing the turbosupercharger from overboosting and destroying the engine at lower altitudes. When the wastegate was closed, the full kinetic energy of the exhaust impacted the turbine wheel, spinning it at speeds exceeding 20,000 revolutions per minute. Mounted on a common shaft, the centrifugal compressor drew in ambient, thin, high-altitude air from a ventral scoop, rapidly accelerating and densifying the charge. However, the laws of thermodynamics dictate that rapidly compressing a gas inevitably raises its temperature. The air exiting the compressor was blisteringly hot, far too hot to feed directly into the carburetor. Introducing this superheated charge into the cylinders would immediately induce catastrophic pre-ignition, shattering the pistons. To resolve this, Kartveli engineered a massive air-to-air heat exchanger, or intercooler. This unit was positioned deep within the lower fuselage, physically located beneath and behind the pilot. The hot, compressed air from the rear compressor was routed forward through internal ducting into the intercooler core. Simultaneously, a separate stream of cooling air was required to extract that heat. This explains the Thunderbolt's distinctive gaping nose cowling. The lower half of that cowling was not for engine cooling, but was a massive ram air intake. This cool, ambient air was channeled straight through the lower airframe to flow over the intercooler fins, extracting the thermal load from the compressed intake charge before being exhausted through variable doors on the fuselage sides. Only after passing through this intercooler was the now dense, cooled air finally routed upward into the downdraft carburetor, mixed with high-octane fuel and delivered to the cylinders. This intricate, heavy and complex thermodynamic loop was the defining characteristic of the P-47. It was an aeroplane built to accommodate its own life support system. While it resulted in the heaviest single-engine fighter of the war, Alexander Kartveli's uncompromising approach to spatial and thermal packaging yielded an interceptor that possessed absolute mechanical supremacy at altitudes where other aircraft simply could not breathe.